Okay, this problem, what's described is that you have a natural gas flame, and it's burning at 1900 degrees C, or it burns at this temperature. And we build a facility next to the Pacific Ocean at 10 degrees C. So now we've got two different temperatures. You can see a cold temp here, and a hot temp, 1900 degrees C. Now the question is about efficiency. We find that we are consuming natural gas at a rate of this much energy per second. I think he means to say it's producing this much energy. We're consuming it so that it produces that much. And discharging heat into the ocean at this particular rate. What's the maximum efficiency that the plant could theoretically achieve? What is sort of implicit in this question is that you understand how engines work, or the efficiency to convert energy how does into work. How does that work? Let me just bring up a graph here, and this is the concept of an engine. You may have seen this in your physics book. So it's the idea that you have a hot reservoir at some temperature T. You have a hot, reservoir at some temperature T. I see I've lost my, TH, and then you have a cold reservoir at some temperature TC, and you extract heat from the hot reservoir, and you use that heat usually to cause some sort of gas to expand, and by expanding it does work. So the pressure time PV is work, what we call it, pressure times the volume, produces work, or the gas would produce work, and then you want to extract as much work as possible, but there's always some sort of waste that's rejected to the cold temperature. So this right here represents the engine concept, and so I say engine concept because this is just a sketch of the flow of energy. So you have QH being converted to work, and then you're getting rid of the sort of additional heat at this lower temperature reservoir. Now that's all very abstract. Let me kind of relate that to a real engine. Here's a 4-stroke engine, and notice that you have the intake stroke, you pull the gas in. The compression stroke, these valves shut, you compress the gas, and usually this is the fuel. And then the power stroke is when you ignite this. So here is where you have pressure. This thing is the ignition of the gas is going to convert from a fluid to a gas. So there's a large volume change and a lot of energy release. So pressure times volume pushes this crankshaft around, turns it around, pushes the piston away. That's power is delivered in that stroke. And then, of course, as it expands, you're using up the energy. It's doing work, so it's cooling off a little bit. And so and it's cooled off, and then the valve opens. I don't like this red here because it's actually cooler than it was here. And then when the piston comes back up, it rejects that gas. Then you pull in some more gas, and you start over and you do it again. So those are the 4 strokes of the engine. Now, how that relates to what we described before is that this is actually, this is the engine concept. You have the hot reservoir, the doing of the work, the pressure times the volume. This is the movement of the piston. So the piston gets, in the power stroke, gets here is attached to the crankshaft. This gets pushed by the gas, by the expansion of the gas. That's where the work is done. And then that expansion also causes the gas to cool, but it still has some heat in it. And then when you open up the valve and push that gas out, that's when the heat is rejected to the lower temperature reservoir. So that's why this is sort of represents the engine concept. High heat work, and then the cold heat, or heat at the cold temperature. Okay, so to deal with this question, what is the maximum efficiency? Well, we know that that's if it were done in a reversible way, which, is probably not. But if it was done in a reversible way, then the equation that we would use is over here, where T, you take the high temperature minus the cold divided by the hot temperature. This is the maximum you can expect. This is actually probably what you have, QH minus QC over QH. So let's work with those equations. So you have the max efficiency, max, eta max equals, I'm going to make this brush a little smaller, TH minus T cold over TH. So this is equal to, now this is all in Kelvin, 1900 plus 273 minus 10 plus 273. And you can see that adding the 273 doesn't really make a difference on the top. But then it does on the bottom, 1900 plus 273. So you have on the top essentially 1890 divided by 2173. So this is roughly, I'm going to say this is roughly equal to, 1890. It's like 19 over 20, very close to that, which is roughly equal to 80%. Let's see. No, 85%. 85% efficiency. This is the maximum possible in this scenario, given those two temperatures. What's the actuals? Well, that is the actual efficiency. That would be the most efficient. What was I trying to say? Oops. The actual is QH. Oh, this is a reversible. If that was done reversible, but we have QH minus QC over QH is the actual. We don't actually have Q. We have joules every second. We have watts. But let's say in 1 second, then we know that QH is equal to 2.5 megajoules minus QC, which is 1 megajoule divided by 2.5 megajoules. So this is, again, these megajoules cancel, so this is equal to 1.5 over 2.5, or 15. It equals 15 over 25, which is equal to 60%. Multiply both by 4 over 4. You get 60%. So the actual efficiency is 60% and the maximum is 85%.